ठीक है, you can start sharing screen now.
Okay, so here we go. Can you see?
Yeah, I can.
I'm sorry. I'm sorry.
Okay.
Now it is fine. Okay. So can we start?
Yeah, you can. Yeah, please go ahead.
So good morning all. So today we'll be discussing on quasiparticles and emergent phenomena, so to say, as the title says. So we'll see how has it come to the domain of physics and when has it arisen, and what are the history and recent advances and the future perspective. So this is the outline. So first we will begin with from a concept emerges, of course, from the Landau formulation of symmetry breaking and all that. And then phonons, then amplitude modes, what is it about, and what is its relation in the condensed matter as well as in high energy physics side. Then Bogoliubov quasiparticles and Magnons, very well-known spin wave quantization, and then the topological defect, and very recently discovered relativistic counterpart in the condensed matter domain.
ज्ञाति, मतलब अभी बैकग्राउंड में बहुत नॉइज आ रहा है क्या? मतलब क्या वो नॉइज थोड़ा सा कम, थोड़ा सप्रेस हो सकता है क्या?
तो एक्चुअली दिस इज द लोकेशन वेयर
कुछ तो शायद वो कुछ ठीक कर रहे हैं घर में, शायद
क्या करें,
मतलब घर में कुछ रिपेयरिंग हो रही है.
outside, but I don't know how it is picking up.
Oh, that's fine then. That's fine.
It cannot be outside. So maybe I'll reduce the sound a little bit.
Yeah, okay? It is better now. But perhaps you can reduce it a bit more.
I'll speak here.
Okay.
Hello.
Yeah. It is better than before.
This is something that I do not have any control over, and unfortunately I'm surrounded by, so like
no problem.
Signal surrounded by noise.
No problem.
Okay, so please I beg your pardon for it, but I am helpless anyway. Okay, so this is the so let me begin with from the concept how it emerges. So, in 1938 or around 1930, the outspoken and the blunt-spoken Lev Landau was imprisoned by KGB in 1930, and he was actually set free by a special request from Kapija, a Soviet very renowned physicist, Kapija, and he actually was put as a guarantor. And he persuaded the capturers, saying that if Landau would be left in prison, it would be a great loss to the Soviet science. And promptly, they actually set him free, and without any surprise. And the year in which he was imprisoned was the year on which the superfluidity was discovered. Okay, so after he released from the jail, Landau, along with the Kapija, they wrote down a paper, and which was a very theoretical landmark for the explanation of the superfluidity, what we now know today as phonon and roton theory of superfluid of helium. Okay, so, and he was the right theorist, probably. Kapija was, of course, a visionary. He knew he is the man who can actually come up with something very special, and he did so. So the concept of this quasi-particle actually proposed by Lev Landau. first time in 1930 in order to explain the superfluidity. And what is it by definition? This is an elementary excitation of collection of particles. Of course, along with his theoretical prediction and explanation, several other theorists have also played a very decisive role. But as the time progresses, the concept of quasi-particle or elementary excitation remains. It prevails. And then in 1950, of course, as we all know, that the concept of spontaneous symmetry breaking in order to explain the phase transition was proposed by Landau in 1950 and 60. We know the concept of order parameter and how the symmetry breaking gives rise to the different phases of the material. That also arose along that time. But apart from all this great event, the concept of quasi-particle did not get the momentum or the credibility what it actually deserved to. Then came the year 1980. The revolutionary experimental finding was happening in the Europe with the discovery of integer quantum Hall effect. And after that, immediately people also discover a fractional quantum Hall effect. So in fact, in order to explain the fractional quantum Hall effect, Bob Laughlin actually proposed that the charge actually getting split while there is a strong correlation between them. So the concept of fractionalization arose then. Concept of fractionalization arose then in order to explain the fractional quantum Hall effect. So this is how the concept of a quasi-particle actually caught the momentum or caught the attention of the condensed matter physicists. It was, and people by now also, by now I mean to say up to 1980 or with the discovery of fractional quantum Hall effect, they don't have any idea whether it is actually a particle or wave nature. Absolutely no idea. And I will also tell you, presently also we have some speculation on some form of the quasi-particle. We absolutely have no idea whether it is a collective excitation or it is a particle aspect which can be dealt in a very similar fashion the way what we are dealing with like our electron proton in the high energy domain. Okay, so the Landau discovery of quasi-particle excitation put this concept in the tangible context of condensed matter physics. This is how the concept of quasi-particle came to the physics, proposed by Landau and subsequently get modified, and they got the different name and appear and reappear in different contexts. So number one, the phonon. So of course, as you all know that photon is the quantization of electromagnetic wave, and that term photon was coined by Gilbert Lewis in 1926. I have not mentioned here, but that concept came much later than the photoelectric effect was explained by Einstein. 1926, Gilbert Lewis, the person who renamed that word.
Sorry to interrupt you. Just a confirmation. As far as I remember, Gilbert Lewis was a person who did a lot of discoveries in chemistry.
Yeah.
Okay.
Yeah.
This was that person.
So very similar to the definition. By definition, it is the quantum version of some excitation. The quantization of electromagnetic wave, the counterpart of the lattice vibration. This is the man, Igor Tamm, introduced the concept of elastic quanta in 1930. Then this is the Frenkel. We all know Frenkel defect and 1 year Mott defect, right? In our defect in solids, if you remember, Frenkel defect, color centers. So he is the man who coined the term phonon as the quantized lattice vibration. And again came this man, Solomon Baker, who said it is the electron and the lattice deformation or phonon is known as polaron, what we very frequently use nowadays. So, and the concept of this is a Fröhlich interaction. If you remember the concept of superconductivity, the two electrons do interact each other with the help of lattice deformation. We call it a Fröhlich mechanism. So we will discuss in more detail how the lattice vibration and all that concept help physicists to explain the Bezier theory. So what generally happen? This phonon very similar to the electronic band structure. We know how the band formation occurs in the solid. It is the overlapping of the atomic orbitals. And the way we have actually understand the concept of conduction band, valency band, and the band gap or the forbidden band gap. The phonon also can have a band gap, and that phonon band gap can also be tuned. So remember the concept of electron. We frequently use the concept of electron in the high energy physics as a free particle. But when it comes to the domain of condensed matter physics, it is no more electron as a free particle. Electron is the name remains same linguistically, but electron is a quasi-particle, because since the days of Landau paradigm or phase transition, electron is a quasi-particle because there are a very strong interaction among the electrons as well as electron with the lattice. So therefore, electron is no more free. So the concept of effective mass actually arises from that discovery. So free electron mass doesn't exist anymore in the domain of condensed matter physics. So let's suppose if you ask somebody what is the mass of an electron, he'll say 9.1 10 to the minus 31 kg. That is correct, but that is in the domain of high energy physics, or at least to be in a simplified way, at least when an electron doesn't interact with anyone, is out of any interaction. But that is impossible even in principle when you are discussing in the domain of solid state physics or condensed matter physics. Invariably, mass of an electron will not remain same. So always you often encounter that word effective mass. That effective mass is coming because of this phonon dress electron. Always.
Gyanti, may I ask a question now?
Yes.
So as you said that the mass of the electron is 9.31 10 to the minus 31 kg when the electron is free. So
yes,
if I take the example of, for example, the hydrogen atom. So in hydrogen atom there is and so you have one proton and one electron, and electron is combined through electrostatic forces with the proton. So is the mass still, I mean, as you said that the mass will change. So how much does the mass change in this case? In case of, for example, the Bohr atom, or sorry, Bohr hydrogen.
Okay.
No, my question is, because in this case, electron is interacting with the proton. So, and as you said that the mass of the electron will no longer be 9.31 10 to the minus 31 if it is interacting. So how much does the mass change in this case?
It's, okay, so let me answer you in a brief way first, and then I'll get into the more details. Speaking in a single statement, it's a very small, because there is only one nucleus if you are dealing with the hydrogen atom.
Mm-hmm.
But here we are dealing with a solid which at least contain 10 to the 23 number of atoms per centimeter cube. So at least it should give a feel for you that how much interaction would be. It's order of magnitude higher.
Mm-hmm.
And if you are interested to know much more than this, then you have to deal with three things. One is when there is a compound or there is a material, there will be a certain kind of bonding. So bonding between the atoms. Bonding between the atoms means there will be the electronegativity between the different atoms. That is one parameter. Number two is the dielectric constant. These two things essentially decide what will be the effective mass of electron in a particular environment.
Okay.
Yes.
So, so if I may ask one more question. So, can I use a word called physical mass? Because I mean, this is what I think, that perhaps the physical mass will not change the mass that electron possesses, but somehow, because we want to incorporate some interactions, that's why we use effective mass. Is it true to say that, or is it correct?
Sorry, your voice now I could not hear.
Actually, I'm saying that is it will it be correct to say that the physical mass of the electron will remain unchanged, but only a quantity called as effective mass, which accounts for the interaction between the electron and other atoms of the lattice, this may change? Is it correct to say that?
That might be another way to look at the thing, but how do we calculate the physical mass of an electron?
Oh, okay, okay, okay.
That is correct, because in the language of relativity, one can have rest mass as well as the kinetic mass. But kinetic mass you can switch off, but rest mass you can do nothing about it. It will remain there as long as its existence is there.
Yeah, so
Because you no more deal with physical mass, rather we deal with energy there.
yeah, of course. Okay, okay. So because if the electron is interacting, somehow the mass is changed, and you cannot really measure the physical mass in that case. So there won't be any meaning.
That is one thing. That is one thing, and another thing, if you remember our elementary quantum mechanics, you cannot individually say this is the kinetic energy and the potential energy, because you are already dealing with total energy. That also hinders you to calculate individually how much contribution is coming from this and that.
So in principle, even you cannot measure that physical mass when the electron is interacting with other atoms, for example. It is not possible
actually,
in principle.
Rahul bhai, I don't know how much justice I am giving to your question, but as far as my understanding is concerned, how do I know that there is this much is the absolute mass of an electron, and this is the additional contribution coming from the interaction and nearby environment? Am I understood your question?
Yeah, exactly.
Okay, but okay, as you said in the textbook also, we used to see what is the mass of an electron, and the mass of an electron is considered to be a natural constant. Natural constant quantity like the charge. So I think the charge of mass of that electron is calculated only by considering its isolation from the rest of the interaction. I believe. So if anybody is getting any sort of variation, whether it is less or more, that they call as effective mass.
Okay. So because perhaps I can always say that even though I'm measuring this as effective mass, and if I can say that the physical mass, but that the physical mass still remains the same, that is the mass that when electron is not interacting with other things. Is this correct?
Physical mass, I don't know how to distinguish it actually from the other things. Okay, that is correct. Means whatever you say, that is correct. So okay, the ultimate method to calculate the mass is from the cyclotron resonance, right? So that is where the mass has been calculated, but that is again due to electromagnetic interaction in a magnetic field. You calculate the mass from the curvature of the elementary particle.
Okay.
Right? Okay. So depending upon the energy and its deviation, you can calculate the mass. So, and moreover, it is under the action of Lorentz force, and it is a Lorentz force means it is a velocity dependent as well as charge dependent. So,
yeah, but that mass would only be the effective mass of the electron. Okay, fine. If you measure it that way, then it is not really possible to measure the physical mass.
Yes.
Okay, fine.
Yeah. But no matter how long you discuss, how clear it may appear, there is always something we don't understand. I believe after reading or preparing this talk. So there is a lot of doubt. So you can ask any question. So at least you can give some insight that I don't understand. And these images nothing but the dispersion relation, very similar to the photon. We have electron photon dispersion in the momentum space. So it's a parabolic dispersion relation in the conventional solids, and it will be linear when it will be relativistic charged particle or electrons. But one thing I just want to emphasize here, that even though electron is written there in a language form, but if you are discussing in the domain of condensed matter physics, please do consider it as a quasi-particle. It's not an isolated particle. which people have an intuition about as far as the high energy particle or high energy physics is concerned. It's not like that.
So, sorry, Gyanti, one more question. So perhaps I missed the definition of a quasi-particle. So how do we really define a quasi-particle? Because you said that electron is also quasi-particle.
Okay. Electron is quasi-particle. Okay, let me tell you, give you one example. So let's suppose we have a wire, and in one end there is a board, another end there is a ball, right? So we do speak very often, what is the current? It is the amount of charge flows per unit time across the perpendicular to the area cross section of the conductor. Is that current density? Thereby we always derive current from the current density.
By integrating over
divided by area. Yes. But in solid, no charge particle, if you have a feel for it, what will be the mobility or a drift velocity of a charge particle in a solid? It's a 100 meter per second or 200 meter per second, something around that. It's not more than that. So now imagine if in a North Pole you have a switch and in South Pole there is a ball. So tentatively, how much time it would have been taken for light to switch on there? It would have been taken a decent amount of time, is it not? But it is not the case. It just takes the speed of light. So that guarantees electron actually not flowing physically. Electron doesn't flow actually. So as far as the Fermi velocity or a drift velocity of a charge carrier in a solid is concerned, it's certainly not the flow of electron physically, as by the definition of current is there, would have switched on the light in that amount of time. So that possibility is ruled out. So there is something else is going on. So there you can actually consider the quasi-particle. It's a kind of excitation, elementary excitation, when there is large amount of particle and which are particle like behavior, but they are not physical particles.
And you said excitation, and so an excitation of what?
Excitation of those elementary particles interactions.
Okay.
So let's suppose in the sea, what are the waves?
Sorry, what was the question?
In sea, what
okay.
are the waves? They are very much water molecule. But here you have to assume that individual water molecule has nothing to do with wave. It's a collective excitation. You have to consider collective excitation.
Okay, perhaps we can talk about it at the end of the talk.
Sorry?
Perhaps we can talk about it at the end of the talk.
Okay. So I have remember this point. So we'll discuss it. But one point I will again tell you, as I also told you in the beginning, there are a lot of speculation and controversy, and there is no unanimous verdict. Particularly in Magnon case, I will tell you in a minute. People doesn't have an idea whether it is a collective excitation or the individual quasiparticles. So I'll tell you in a moment.
No, perhaps before you proceed further, I mean, so my question was like, or maybe I missed it. How do we define a quasi-particle?
I have mentioned here. It's an elementary excitation of all collection of particles.
Okay, fine. Oh, sorry, I'm sorry, I missed it.
Yeah, no problem. So then, okay. So this is a very conventional and very obvious thing, and I think it's a well-versed terminology. Phonon, it's everybody is familiar about. So now the amplitude modes. It's a bit mysterious and not that obvious. In the early 1950, again, these two fellows, Ginsberg and Landau, they were trying to explain the superconductivity, because the superconductor discovery was at the topmost priority. So they are anyway trying to explain it. But how they're trying to explain it? They're trying to use the concept of quantum field theory and concept of spontaneous symmetry breaking together. And they were trying to explain, at least to what is the microscopic origin of the superconductors? So what we know today as Ginzburg-Landau theory. Okay, the very same idea was again taken forward by Lambo and Goldstone. Spontaneous symmetry breaking, and you know rest. Spontaneous symmetry breaking. If there is a breaking of global spontaneous symmetry, then you can come up with a massless excitation, massless particle, which we call the Goldstone mode, Goldstone boson. You know, but you don't see Goldstone boson anyway. Massless particle except photon. So that time it was a controversial claim. But Anderson somehow managed to come up with another mechanism and successfully could explain why the boson getting mass. So the concept of Higgs mechanism, what we know now today, has actually started from here, Ginzburg and Landau. Then Keeble and other, and of course Peter Higgs and Ingloit and Robert Brown, all those three also claim how the spontaneous symmetry breaking of the gauge field can subsequently could give rise to the different masses to the different elementary particles. So you know what is this? This is the energy density product parameter, and this is known as phase and amplitude modes in the condensed matter physics. And very surprisingly, I got to know from history, condensed matter physicists doesn't have an idea. High energy physicists are pursuing for the elementary mass along this line, because all these people are actually condensed matter theorists. They knew nothing about the high energy sites, but all of a sudden they got to see the Peter Higgs paper, and I was taken, and subsequently, you know, the thing has been discovered. So this what we are calling as Higgs mechanism. Higgs mechanism. It was actually known as amplitude modes in condensed matter physics. And where can you get that? Very similar to Higgs mechanism. You know much better. Similar kind of energy density diagram one can see in superconductor also, and they are known as amplitude modes. And also you can see similar kind of arrangement in ultra cold atoms also, if you study. So this idea actually was borrowed from the condensed matter sites. So this is another excitation, Goldstone mode. Okay, this is another quasi-particle in superconductor and high energy physics, but of course they both are energy-wise poles apart. But people are expecting someday there will be one-to-one correspondence between the Higgs particle in the condensed matter setting. There is no Higgs particle in condensed matter setting. So people are trying to find one such, at least in low energy domain. Okay. So this is the extension of that. There is another quasi-particle known as Bogoliubov quasi-particle. So people, Leon Cooper, 1950, you know, the person who actually proposed that mechanism, Baden Cooper and Stepper theory, Cooper pairing. These two, Nikolai Bogoliubov and John Valentin, they actually were trying to study the excitation happening in the superconductor. And surprising what they found if you do excite a superconductor, you will end up with a fermionic quasi-particles. And what is the fermionic quasi-particle? It's a linear combination of electron and holes with opposite spin. And it was surprising. And they actually, if you see, this is the experimental finding that the conductance ratio of the superconductor excitation quasi-particle, and this white region, you can see, these are the Bogoliubov quasi-particle studied in inelastic neutron diffraction, in inelastic neutron scattering. It was surprising. This is another kind of quasi-particle.
And what are these black regions?
Black region.
Yeah.
Different energy. They are showing the different contrast. So one is electron, one is hole.
Okay. And the white one is this Bogoliubov quasi-particle.
Bogoliubov quasi-particle. I mean, if you do excite a superconductor, you are inevitably going to break the Cooper pairs, because you know that Eg equal to 3.5 kbtc, na? If you remember what is the superconducting energy gap? Two electrons are actually forming Cooper pair through the lattice vibration. If you do want to separate them, you have to provide some energy from outside as a perturbation.
Okay.
And if you do so, you will end up with the one electron, one hole with opposite spin. And the concept was first found by or predicted by Bogoliubov. That's why often when it comes to the superconductor discussion, people often discuss Bogoliubov Hamiltonian, and this is the Quasiparticle, Bogoliubov Hamiltonian, very renowned, well known. This is one. Then the Magnons. So what is the Magnons? Magnons is actually the concept was proposed by Felix Bloch, first director of CERN. So he proposed actually a spin wave. If you imagine a magnetic material and a long range magnetic order is there. So, but individually, if you do see an electron or an individual spin, it will be preceding about a fixed point, right? And now, if you consider a one-dimensional chain in a magnetic material, they are preceding in a particular order with a particular frequency. We call it Lamar's frequency. Okay. Now, if you actually create a minute disturbance in any of individual spins, it will transmit to the neighboring spins, and subsequently and eventually it will go to the other end. That means a spin wave as a propagating disturbance of the precision of the spin through the lattice in a magnetic material. A minute change in the precessional frequency can be considered as a disturbance and can propagate all the way to the other end of the chain, and that is known as spin wave. And a collection of all those waves or excitation is known as Magnon. So now, characteristic, it's still under controversy. Hello, Lalbhai, your voice is not audible.
I'm saying that we could not hear you for 10 to 15 seconds in between because of some network issue.
I'm telling, actually, whether the magnons are quasi-particle, which are very much similar to the particle, or they are actually collection of all excited waves, is still under controversy at present also. But this is the concept first introduced by Felix Bloch to explain the spontaneous magnetization in all the magnetic materials. And experimentally, it was found by Burton Brockhaus by using Newton diffraction. That is experimentally verified. But when it comes to the definition of the quasi-particle, it doesn't satisfy, so to say. Whether it is an individual particle or individual entity which has a fixed location, or it has an extended location like a wave, it is under controversy. Okay. And of course, in quantum matter physics, people are trying to exploit this beautiful feature of all the magnetic materials in order to actually come up with some the low energy loss devices, which are called as magnonics, like spintronics. They are calling it magnonics. So explore the thermal behavior of magnetic material to come up with something where the energy loss will be very less. And then the topological defect. Again, this person, Tommy Sky, the concept is very, very unique and new. Of course, to me, it seems totally unique even today. So one can easily imagine how it would have been in those days. So the question was simple. How come from the continuum of this space-time, a discrete charge particle or a discrete elementary particle could come? The question was this. And he said, although elementary particle could probably be explained by considering them as a geometrical distortion in the continuum of space-time. And geometric twist. So like a Mobius strip, you know what is the definition, and they do possess a topological feature. That means you cannot deform them continuously from one topological phase to another phase without actually breaking the rules or without changing the topological number. And in the condensed matter physics, one such topological defect is magnetic fermion. You all know that. And what is that? You can see in the picture. The background is very formal, uniform, but sometimes it feels like there are actually chiral spin texture in the background of uniform spin arrangement. They call it magnetic fermion. Okay. And which has been verified experimentally even at a room temperature, and the material is very simple. Material is very simple. MNSI, one can do it in lab, and one can see it by using Lorentz microscope. Okay, but the thing which has not been verified experimentally but proposed theoretically is cosmic string, what Raoul is much more familiar with, and magnetic monopole. So these are considered to be the topological defect in cosmology. That means they do possess something as some topological feature which is very robust with the local perturbation.
Actually, I've seen some papers on cosmic string. I mean, there are a lot of papers on cosmic string. They keep coming almost every day on archive. But now, since I know that they are somehow related to these things, which I already know, I'll have a look at them.
Yeah, I'm actually trying to tell you the number of quasi-particles or the number of zones or domains in which the people have actually borrowed the idea of quasi-particle to explain at least some extent what could possibly have occurred. Okay. In some cases, fortunately, experimental evidence have been found, but in some cases, they are yet to be. And the last one is the relativistic fermions. And the relativistic fermion, you know all that. So electron in a solid, the highest speed at which an electron moves in a material is in graphene. The Fermi velocity of electron is 10 to the power 6 meters per second. Is like 0.9 times speed of light. Okay, this is really high, and this ultra high mobility or very high Fermi velocity is the consequence of linear band dispersion relation. You cannot have a parabolic band dispersion and that high Fermi velocity. You cannot have. So that's why I told na, you cannot have a copper wire connecting from North Pole to South Pole, and you can switch on the light with the speed of light. Your definition of current doesn't hold good there anymore. So that is another indication of existence of electromagnetic wave or field. It is not the current. So current definition doesn't satisfy that experimental, cannot explain that experiment. So that's a beautiful thing. And these are the three different relativistic fermion, you know that, and all of them have been experimentally verified very recently, and they're all are at the limelight. And this quasi-particle, nobody knows it is the end of this quasi-particle chain, or there are many more to come. But of course, understanding about the condensed matter physics by invoking the concept of quasi-particle is just amazing. It has given us a lot of flexibility and understanding to understand the complex behavior of elementary particle in the low energy physics, which would have been extremely difficult otherwise in high energy domain. So putting it beyond doubt, the concept of quasi-particle provides an invaluable tool for describing the complex emergent phenomena seen in the condensed matter. Thank you. So this is
Thank
what
you
I
for this,
could
sir.
prepare in a hurry, because Nikhil told me yesterday, sir, I'm not okay health wise. So I said, so someone else has to go unhealthy then.
Yeah, it was a good talk. Now I mean, at least one thing or one message I could take from here is that somehow the notion, I mean, that these two fields, the condensed matter from where, or I mean, so it is related to quasi particles. So is it true that the notion of quasi particles has come from the field of condensed matter?
Sorry, Rahul bhai?
I'm asking, is it true to say that the notion of quasi particle has come from the condensed matter field?
Yes, yes, yes.
Okay, yeah.
Because
So
the founder, the predictor, or the first claim came from the lab Landau only.
okay, fine.
And that's what I told you, that in order to explain the superfluidity only, he proposed that concept.
Okay, fine.
Many other theory took over as the time goes by, but the concept of quasi-particle actually remains.
Yeah,
And
sure.
subsequently, people have renamed it in the different context and different mechanism, but the idea remains.
Okay. So then it would be good if maybe I can try this. I mean, I haven't gone through any of the papers that say something about cosmic strings, but maybe I can try at least to speak about cosmic strings in future talks.
Yeah, it's a very good thing, people. But one thing, as far as my understanding is concerned, I'm not convinced that, as you asked, what is the quasi-particle and what is this excitation you are talking about? So, if I could see the virtual image, if I can intuitively remember. So they used to put, if there are a bunch of electrons that do interact, and they will give like they will give rise to a ghost-like particle which doesn't have a very periodic or a very nice shape, but they will call it a ghost particle. Many occasions I have heard it from the specialist. They call it ghost particle.
Yeah.
Now imagine, let us discuss this very elementary thing what I told you. This is the length of the wire from north to south pole. It is nothing more. Electron are in motion in a conductor. Lattice doesn't move. It's an electron in motion. So in order for an electron to move, it definitely going to take a definite amount of time.
Sure.
But that time has to be significantly less as compared to the speed of the light. If you do compare,
it will be larger.
is it not?
The
Yeah,
time
because electron is a physical particle, and it has to overcome all those scattering events while passing from one end to another.
Yeah, true.
And 10 to the power 23 number of atoms, and the copper atomic number is 29. You multiply that many number of electrons, and the probability of scattering is just a gigantic number. And for an electron to go from North Pole to South Pole would have taken billions of years. Because that is the reason why photon from the center of the sun to photosphere takes 1 million light year, but from photosphere to planet Earth just 8.5 minutes.
Okay.
It's all about scattering. So that means our textbook keeping definition that the current is flow of charge per unit time held perpendicular to the area of cross section is wrong. That is not current. If it is the current, then the current is being carried out by a ghost particle. So only the concept of quasi-particle can save the definition.
But I mean, I have also read these explanations. So as far as I remember, they say that these kind of drifting. So although the drift velocity, as the word is used for the electron, as the drift velocity is of the order of some centimeters per second. But then these these kind of driftings will happen at all places in just one go. So whenever you turn on the switch, these kind of driftings will happen each and every place in the wire that you are observing. So that's why so as soon as you turn the switch on, you just get light.
But that's what I'm saying. But can that explain the amount of time takes for to switch on the light? It cannot.
I mean, so in my opinion, the two are different. So one is just the definition of current. So current is let's say I equals dq over dt, the amount of charge that flows through some cross section in a given amount of time. You just divide the two and you will get the current. So but what I know is that as soon as you switch the as soon as you turn on the switch, these kind of driftings of electrons will happen in all places in the conductor, and that's how the the bulb will switch on almost instantly. So
One thing. I understood your thing, but I just want to get a clarification. But the charges are discrete in nature. Suppose charge A has a drift 5 centimeter, charge B has a drift another 5 meters or 5 centimeter. But how do they connect each other to for the current to flow? The path has to be continuous.
it's not okay. So I may have to provide more details, but this is what I understood from the explanation.
But one thing, but there is a twist. You can save your argument if you can say an electron is actually an electron of all the atoms present in the system. That electron doesn't belong to individual atom. If an electron actually being confined to a particular nuclei because of Coulomb interaction, then at some extent, after some extent, that electron doesn't allow to move anymore.
Yeah, that is true. That is true. But I think I said something different. All I'm saying is the the drifting of the electron will happen in all places in just one go. So as soon as you turn the switch on, it will happen at all places at that particular moment. So that's why the so okay, perhaps this I'm not sure this is the correct way of saying it or not. But then let's say this is your one end where you have the switch, and this is your other end where you have the bulb. So just in the vicinity of the bulb, the electron will also drift away inside the bulb, and because of that, the bulb will just glow. And okay, but the bulb will also need some continuous flow of electrons.
But had it been that, once I switch off the light, the bulb should remain glow for some time, nah? Because already that kick has not reached to the electron which is nearby to the bulb. Whether the power has been switched off, that information has not been passed to the electron nearer to the bulb.
Yeah, but that information, I mean, so in that case, okay, so I think I need to verify this, but this is what I know. So that information that the electron has to drift. So so that okay, so let's say at t equal to 0, you turn the switch on, and
Okay.
then from that point, the information will travel throughout the length of the conductor at each point at each point of the conductor with the speed of light.
One thing. So you are telling the information, of course, as we all know, information at max can propagate at the speed of light, right? Suppose at the switch end, electron is instantaneously communicated, you have to move. The race has been started. But the electron which are sitting very close to the bulb at the south pole doesn't know. So
Yeah,
unless the information has passed to reach to that electron doesn't care.
Yeah, that is true. But I'm saying is the information to that electron has reached with the speed of light from the point. So at t equal to 0, you turn the switch on, and at that moment, the information.
So I understood. That's what I'm saying. You are telling. So let us touch all the electron and say, hey, you have to move. It's time to go. Instead, I'm saying it's the field moving. The very same thing. Unless field is moving and passing them the information, they don't care because they will take their own time to communicate.
And when you are saying field, which field are you talking about?
Let's suppose at the end.
Field means the electromagnetic field.
Yes.
Okay.
In what way you will communicate your message or information? you switch on the light.
Mhm.
So information has to propagate in a given mode. What will be the mode of propagation? So
Electromagnetic wave.
you are telling I am passing on the information to every individual electron. But I think that will also get a lot of time, even if you do what I need to say. Even if you communicate the information to every individual particle, it will take enormous amount of time. And moreover, even if they try to move immediately, they will encounter the other nearby electron. So scattering is inevitable. So somehow you will get a time lag. I think.
Okay. You need to think about it a bit more then.
I think. And moreover, light is okay. If all the electron wherever they are, they start uniformly moving forward, opposite to the direction of the potential, or sorry, but lattice vibration will hindrance their motion, will not it?
They will. They will.
So if the distance is really we are dealing with the north to south pole, it should take really some amount of time. That has been tested, I think. But if only you take the field into consideration, the passage of information, you have to go now. If it is passing through only by electromagnetic wave, that matches exactly to the time it takes. Maybe it's a very good point. We can discuss much more on this.
Over the telephone, perhaps.
But it's a very good point. So this is why, anyway, I'm happy that the presentation has triggered some discussion.
Sure. Sure. So, Richa and Nikhil, do you have any other questions to ask?
I don't have.
Okay. Please go ahead.
I don't have.
You don't have? Okay. Okay.
Yes,
Fine.
because
And-
I am
and-
not very much like I need to watch it again. Then I will like maybe understand something.
Sure. Mhm.
Not every individual can ask because we may argue. I have heard, or we in fact have heard. Rahul bhai, you might have several experiences. We have